to compare the solution sets between a strict equation with absolute value, a conjunction, and a disjunction. And there are two methods for solving. And one is graphically, and the other is breaking into two equations. So I will give you the two, just jot this down, two methods for solving. One method is by graphing, and I'll give you a clever little way to graph these. And the other method actually has a name. It's called bifurcation, and the prefix bi means two. So that just means you're simply breaking it apart into two separate equations and looking for answers, arriving at your answers by splitting it into two separate equations. But it actually does have a name. So let's go through the methods here in this video. And of course, I will hold you responsible for knowing both. All right, if I have a strict absolute value, this is an equation. So to use the bifurcation method, which just means I'm solving two equations, I simply take what's given, 10 minus 2x equals 6, or, this is my other equation, 10 minus 2x is equal to negative 6. So I change the positive 6 to negative 6. I set it equal to the opposite value. And then I solve each piece. Negative 2x is negative 4, therefore x is positive 2, or negative 2x is equal to negative 16, x equals 8. So I now have a discrete solution set. It's not continuous, and discrete meaning it's countable. So my solution set in set notation would be the points 2 and 8. The points 2 and 8. Now let's look at this as a graph. Another method is by visually viewing the graph, or using the graph to actually solve. So a graphing method, you would take what's inside the inequality, so this is going to be my graphing method. I would take what's inside the absolute value bars, and I would say 10 minus 2x equals 0. I would figure out which x value would make that 0, and that would give me x equals 5. So on a number line, I would mark myself as 5. So the center of my world at the moment will be the point 5, and anything coming away will come from 5, and I will count out in both directions an equal number of spaces. But the way to determine the number of spaces that you will count, I have 6 and I have a coefficient of 2 on x. I'm setting this equal to 6. The coefficient on x is 2. That simplifies to 3. 5 is the center. That means I'm counting 3 units in the positive direction from 5 and then 3 units in a negative direction from 5. 5 plus 3 is 8. 5 minus 3 is 2. So by graphing, I've arrived at the two solutions as well. So to recap graphing, you take what's inside the absolute value bars, you solve it for 0. That becomes your center for this particular problem on the number line. And then to figure out the number of units to the left and right of that center point, whatever the equation is set equal to must be divided by the coefficient on the variable, and that tells you the number of units to count in both the positive direction and the negative direction. And that allows you to quickly hone in on the 2 points that make this true. So we've decided that in this particular problem, the first example, my solutions are the points 2 and 8. And when I have a strict equality, my graph looks like this. Just 2 points, 2 discrete. This is a discrete solution set, meaning it's countable, it's not continuous. It's a discrete solution set, 2 exact points. It is not a continuous range. Conjunction, on the other hand, well, to solve this as bifurcation, you take exactly what's given inside the absolute value bars and you solve it as it's given, completely intact. And then the other equation that you set up, you have 10 minus 2x, but now you reverse the inequality symbol and you set it equal to -6. So you can see the subtle changes. And then you solve each one down and you end up with x is greater than or equal to 2. And you have, I should have used the word and instead of or because this is an and x is less than or equal to 8. The same boundary points as before. But the way that you set up your solution graph is different. I have 2 and I have 8. Both boundary points are included in my solution set. Since this is a conjunction, meaning I'm looking for overlap where they're both true, my boundary points and the points in between are my solution set. So it's still basically very similar to solving for the absolute value equation. I have the same boundary points, but the way my solution set looks is different. And let's do the disjunction scenario. And I will leave my graph up. Okay, for disjunction, very much like conjunction, everything remains the same for bifurcation. 10 minus 2x is greater than or equal to 6, or 10 minus 2x. Now I reverse my inequality, less than or equal to -6. And solving this down, I end up with x is less than or equal to 2, or x is greater than or equal to 8. To set up my graph to represent disjunction, you can see my boundary points are still the same. I have 2 and I have 8. X is less than or equal to 2. Well, that I'm coloring in solid boundary point, shading in the direction of -infinity. X is greater than or equal to 8. Solid point at the boundary, moving off in the direction of +infinity. So I wanted you to view all three graphed solution sets to see how they're similar and how they're different. The way you find the boundary points is exactly the same. You can use what's called bifurcation, where you solve two separate equations. One equation is exactly as given without the absolute value bars, and the second equation is exactly what's inside the absolute value symbol, but you reverse the inequality symbol and you set it equal to the opposite of the number. It gives you the same boundary points all the way across, and solving it with bifurcation, you get the correct inequality symbols, and now you can visually see the graph, how the graphs are the same, they have the same boundary points, but a strict absolute value has discrete, just two little points that are solutions. The conjunction and disjunction have what we call the continuous solution set, where you're shading on a range. So it's a continuous solution set over a range. So that's a basic example of how to do one of each type.